Morning. Welcome to Krishna's class. Let's continue with our explorations of measurable functions. Now we would like to work on what are called sequences of measurable functions. In real valued or extended real valued functions, we are considering for the moment. Then you can talk about the functions, the limit supremum of a sequence of functions which exists, limit infimum of sequence of functions which also exists, and limit of a sequence of functions which may not exist. And then of course measurability, how the measurability of the sequences would assure the measurability of the limit supremum, limit infimum, and limit if it exists. So these are the things that we consider in this lecture. So before that, we would first look at sequences. So sequences of real numbers. For this, we define what is called limit supremum, limit infimum, and limit if it exists. So definition, let An be a sequence in the extended, that means they are extended real numbers, and put Vk equal to supremum of for k equal to that means we omit the first k minus 1 elements and look at the remaining collection of numbers and take the supremum of that. Now you see that a bk minus 1 would be the supremum of this set along with ak minus 1. Therefore, it's quite possible that number would be bigger than pk. So we will have pk. In fact, we have a new sequence. We have a sequence bk such that b1 is greater than or equal to b2 etc. So b1 will be the largest possible number that you have, and b2 will be less than or equal to that, and so on. So it's a sort of what you call a decreasing sequence. So from the given sequence AN, we have constructed a new decreasing sequence. Now, clearly, we shall write beta infimum of so we take infimum, and this of course exists. And call that, so beta is the upper limit of AN, and we write beta to be equal to that's the definition of the limit supreme. So beta is called the limit supreme, is the upper limit of this AN, and this is called when this beta is as defined above is called the limit supremum of the sequence AN. So that's the definition. Now let us try to understand this first of all. Okay. Consider so we take some examples. First example. In the first example, we consider the following sequence. Minus 1 to the power n, 1 by. So if you examine this, it's like this: 0, minus 1, 1. Now you see the first element of this, that is when for n equal to 1, you see that a1 is equal to minus 1, a2 equal to, it is a positive number, it's half. a3 equal to minus 1 by 3. So it goes like this. So from here to here, then this is 1 by 3. Then it comes to 1 by 4. 1 by 4. Then you go to 1 by 5. Minus 1 by 3. Minus 1 by 5 and so on. This is how the sequence starts. You can actually feel what is happening. Starts with minus 1, goes to half, minus 1 by 3, 1 by 4, minus 1 by 5. So for odd values of n, it is going to have the minus sign. Therefore, the sequence we can write now, it is minus 1, 1 by 2, minus 1 by 3, 1 by 4, minus 1 by 5, and so on. That is, you have B1, see, B1, which is the supremum of, what is it, minus 1, 1 by 2, minus 1 by 3, and so on, and that's equal to 1 by 2. B2 is also equal to supremum of 1 by 2, minus 1 by 3, and so on, and this is equal to 1 by 2. Now B3, likewise you can compute. B3 is going to be 1 by 4. B4 is going to be again 1 by 4, etc. So what you get, the sequence that you get is Bn. So starts with 1 by 2, 1 by 2, 1 by 4, 1 by 4, 1 by 6, 1 by 6, and so on. So this is a decreasing sequence. Now what we take is the infimum of this. So your beta is now the infimum of and this turns out to be infimum of this is going to be 0. So beta is equal to 0. Okay, therefore limit we have in this case, limit supremum of An in this case is 0. So this is what we obtain in this particular example. It's a very nice example to illustrate what goes on. Okay, now we take another example. So we take the second example. Second example is An equal to minus 1 to the power n. 1. Or simply minus 1 to the power n. What is this? When this is equal to A1 is equal to minus 1. So that means the sequence AN minus 1, then plus 1, minus 1, 1, minus 1, 1, minus 1, 1. Alternately, minus 1 and plus 1. Now in this case, let us compute B1. B2 equal to 1, B3 equal to 1. It's a constant sequence. Okay. Therefore, Bn is equal to the sequence 1. Now, so what do you get? So this is equal to so you define beta. Which is equal to okay. So in the second case, this is equal to 1. Now let us go further and define what is called limit infimum. Now limit infimum. Therefore limit infimum. Let's define this. Let's define this. So we define limit infimum to minus of that means you take the sequence AN, change its sign for every element, thus you get another sequence minus AN, and then apply your technique of finding the limit supremum, and then take the negation of that number. Whatever you get, that will be called the limit. So this is the definition that we are doing. One can as well build up a definition of this kind, but that is not necessary. Now one observes that, so we go back to the examples. In example 1, if you work this out, limit infimum this is equal to minus. And limit infimum equal to 0. In example 2, limit infimum so in the first example, we have the limit infimum equal to limit supremum. Okay. Whereas in the second example, you see that the limit infimum exists, limit supremum exists, that anyway exists. That's easy to see. But they are not necessarily equal. So these are the two cases. So we make a remark here. The limit supremum A in example 2, limit infimum, limit supremum of An in example 2, limit supremum of An equal to 1 and but both limit supremum and limit infimum always exist. Any An see, we see that these Bns that we have constructed is a monotonic sequence. Therefore, the limit exists. Okay? Right? So we make use of that. Right? No, it could be plus infinity, plus infinity and minus infinity, depending on the sequence that you choose, etc. Now, what further thing that we can assert is the following. Now, if beta is as n tends to infinity, then there exists a subsequence n which converges to beta. Similarly, a similar statement holds about limit infimum also. Converging to the limit infimum. So, but one cannot say that the whole sequence always converges to this. For example, you take in example 2, subsequence converges to n. Similarly, the subsequence converges to so this is the scenario that you have, but they do not converge to the same number. Okay, right? So we can define the sequence AN converges if the following is true. That means limit supremum limit infimum n, which we call, and if they are equal, we write this as limit n tending to infinity Now you see that in example 1, limit n tending to infinity an equal to 0. The limit exists. Whereas is not equal to minus 1, which is the limit infimum of the implication is that the second sequence does not converge. So this sequence does not converge. So that's an example, and that gives a sort of typical situation that we encounter. Sequence need not be as nice as that, but in general it can. So the moral of the story is, for any sequence an, the limit supremum and the limits infimum exist, and the limit exists if and only if the limit supremum is equal to the limit. Okay, now we leave the sequences and go to functions. Okay. Now we have x xm and y equal to. Now we talk about functions. Fn mapping x into for n equal to. Now for each x, we have the number sequence Now we can talk about the limit supremum and limit. Keep x fixed and then talk about the limit supremum and limit. Okay. So these are all extended real valued functions that we are now talking about. Now we define supremum of Fn at x as supremum of Fnx as over n. So supremum of Fn at x is defined as supremum of Fnx for every x belonging to x. This is the definition I have for the supremum function. Similarly, and consequently, we can define now what is called limit supremum. Now we define which is a function evaluated at x equal to b that's the definition of the limit supremum. Similarly, we can define now limit infimum So limit infimum and two functions are now defined for the given sequence of functions, namely the limit supremum and the limit infimum. These functions may be equal, may not be equal. But certainly such functions do exist, because for each x, see these limit exist, so you can fabricate a function which you call the supremum of fn over x or limit supremum of fn at x. Okay. Similarly, you have limit infimum of fn at x fabricated using the limit infimum of the numbers fn x for each x. So these are the definitions of two new functions, which is called the limited supremum and limit infimum. Now, if they are equal, the limit exists and we write this is the definition of fx. If the limit exists, I mean it's not something that can be assured, it depends on the function. It may exist for some values of x, may not exist for some values of x, and so on. So all sorts of variations are possible. So we say that the limit exists provided for every x belonging to x, limit n tending to infinity fn x exists. So wherever it doesn't exist, you don't have such an fx defined. Whereas you have the limit supremum defined, limit infimum defined at each point. So you have some new functions which you get, but they may not be equal. So that's the problem that you often encounter. Okay. But if the limit exists, namely the limit supremum for each x and the limit supremum for infimum for each x are equal, then you say the limit exists and you have the function f defined. So that is what you call the limit. Then you write fx equal to the limit n tending to f. I mean, this is just a mere extension from using the limit supremum and limit for sequence of numbers. to the case of functions. But this is important for every x. We make a statement that such a limit exists, or is the point-wise limit of sequence. Then we denote it by and f is called the point-wise limit of the sequence. It exists, then we denote it by fx for every x, and f is called the point-wise limit of the sequence. Okay. So now the natural questions that you ask are the following. Put one more property to it, namely, we now take every fn to be a measurable function. That's why I said I started defining it. And up to this, it is not required at all. But now we need, you have x, a measurable class of functions, or a sigma algebra on it. Then you have, you are talking about now we have fn from x to y. Now you can talk about measurability because this is a topological space. Okay. So the inverse image of open sets belong to M, then such functions are measurable. So we further now we assume each fn this is the assumption that you make. Each fn is measurable. So we are bringing in a new condition on it. Now the question that you naturally ask, you have now a sequence of functions which are all measurable functions. So the natural question that you ask at this stage is, you know that limit supremum exists, limit infimum exists, and sometimes the limit exists. So the question that you ask is, then you see that automatically limit infimum is also if it is measurable, limit n tending to limit infimum that is because if Fn is a measurable function, minus Fn is also a measurable. And then you apply the definition. Okay. Therefore, our question now is the limit supremum a measurable function? Or is the measurability of Fn's is inherited by Fn? Now you see, we will examine this in the following. So some exploration. Suppose f and g are two measurable functions. Then we observe that maximum of can define a function is so also it's measurable. So let us work it out. See, we will just use our pictorially try to understand. To get a visual picture of the problem, we'll take so we are working on extended real valued functions on okay. So let us have the graph of these two functions. Which you take as later you can replace this or symbolically this line may be taken to represent the whole of x, whatever be the x that you have, which is a measurable set. Now let me draw the graph of two functions. One so let me take a function whose graph is this. This is we color code it. This is G. Now what is F? How does the function, suppose h is equal to what does it look like? See, on this portion, see it is this one up to this, then it is this is this function on some portion, and then over here it is picking up once again from F, and then here it is picking up from G. So for each point x, you take the maximum of fx and gx. So what I have drawn with this yellow thing is the function that you have. Okay. So this is your now we take some alpha. Let us take some alpha and then look at this one. This is the set. Okay. That's this. This is the set. Alpha. This is the set vector. So, when we say measurable, f is measurable if f inverse of belongs to. Similarly, G is measurable This is the measurability of F and G. Now what about H? Now you see that we will try to find out what H inverse of now we will work out this. So H inverse of this is equal to, actually this is your H. Okay. So it is the union of, so you are taking the portion above this. Okay. It is the union of F inverse of and G inverse of as you can visualize in the picture, in the figure. So in this case, what happens is the way in which alpha is chosen, the whole H is above that. You can choose an alpha somewhere here and make it more realistic. Okay, so we will take alpha somewhere. Take this. So this one, Okay. Now I can do. I take alpha to something here. This is alpha. Now you can see where this function f inverse of h inverse of alpha x is. See, this is where h is. So it involves this part, then it involves this part, and then it involves this part. So it is actually this union this union is these three portions. Okay. So this is h inverse of this is also h inverse of now these three portions together. But what is f inverse of? F inverse of see, f is this one. So it is this one. It is this portion there. Then this portion is there. Yeah, this portion is there. And then of course you have this portion is there. This portion. So these are this one as well as see from here to here, this portion and this portion. Now what about G? G greater than alpha is over this portion. I'll mark it. The other color. So you have this portion and this is up to this. So this is the domain where this is going to be. And here again coming here. So this portion is not included in that, and this portion is again equal. Okay. So you take these three portions. Now, one I will mark with this one portion. Then the other one I will mark the other one, let me mark here. So it will come from here, here, and then third portion for F is going to be. What about G? For G, it is this one, and this one. So this whole thing part is this. Now you see that. What about H? H turns out to be the union of H inverse of alpha infinity turns out to be the union of F inverse of this. So this is actually the portion that you have. Then you have this one and this. So you can easily see that this is the situation. So this set is one. You take an example and easily mark it, and I hope it is clear from the figure and my explanation I gave. So what is the conclusion? The conclusion is that alpha is arbitrarily chosen. This is measurable, therefore their union is measurable. Is measurable, which implies F inverse of which is equal to H inverse of that is H inverse. This is true for every alpha. So the union of, the maximum of F and G is measurable. Now we extend this argument. Take a finite sequence F1, F2, etc. Fn, and then you see that the maximum of F1, F2, etc. Fn is measurable if all these Fi's are measurable. Now extend it to the infinite. So let us now state the theorem. Okay. So the theorem is this. Is measurable etc. Then G equal to supremum and H equal to now you can see that. So proof is this. G inverse of this is equal to alpha infinity for every alpha belonging to minus infinity. This is the crucial one. Now you see that the measurability of Fn means this is a measurable set. You see, it's a countable union of measurable sets. So G inverse of alpha infinity has been written as a countable union of measurable sets. And if Fn is measurable, then G is measurable. So it follows from this. Now, you see that the set of G1, G2, Gk, etc. which is a decreasing sequence, are functions which are measurable. And from that, if you take the infimum of all these functions, they are also going to be measurable, or the limit of this supremum of Fn. Similarly, one can prove that the limit infimum is also measurable because it is related. Okay. Therefore, the measurability is now completely clear. Okay. Or the limit supremum, limit infimum, and if the limit exists, the limit of a sequence of measurable functions is measurable. That is the conclusion. Now, another result that you can establish is the following. Just taking. We have the following result, namely the limit of every pointwise convergent sequence of complex measurable functions if it exists. The limit exists. Now, a complex measurable function has the real part measurable and the imaginary part measurable, and using them you can construct the limiting function if it exists, because this is what you have. Fn. Now you see, if Fn is measurable, both real Fn and imaginary Fn are measurable. So this particular sequence is a real sequence. This is also another real sequence. And if the limit of Fn exists, then what happens? The limit of real Fn and imaginary Fn exists, and this is equal to, which is equal to real F now real Fn converges to real F. Imaginary Fn converges to imaginary, and these are measurable functions. Therefore, their limit is measurable if the limit exists. Therefore, these two are measurable functions, and then this combination is a complex measurable function. So that is very simple. Okay. The second part is that are measurable functions. The range in, that means extended real valued functions, then maximum of ft and a minimum of ft are measurable. That we have already examined, and you are convinced that because you can easily write down the first thing as the union of two sets which are measurable, and the second one is the intersection of two sets which are measurable, choosing alpha to infinity. So that is not difficult, and in particular, F plus defined by maximum of 0 and F minus defined by minus of minimum of F0. R. We can use the previous one. This identically zero function is a measurable function. Okay, and this can be easily. This also can be written as minus of maximum of minus fx 0. Okay, so this can be written as s of maximum of minus f and f plus and f minus the positive and negative parts of and we have what you have is mod f is equal to minus and f is equal to. So this is again mod f implies mod f and if f is measurable, then mod f is measurable. Okay. See, this is of course, look at the definition of this. Plus and minus. So this is somewhat optimal. See, this breakup positive functions is not unique. Why? Take a g which is greater than or equal to 0. Then you see that f can also be written as minus. See, both are now positive functions. So you can change these two functions, these components, by adding a non-negative function to it. Okay. Once again, there are several ways in which you can split this. So in some sense, this is a sort of minimal representation. I mean, this is a sort of minimal representation in the sense that we are taking maximum of fn0 and minimum of fn0. Okay, so we have a small result which follows immediately. G minus h, where g is greater than or equal to 0 and h greater than or equal to 0. Now you see this is a breakup of this kind. It's not the same g that I am using here. It's a different g. Okay, now this is quite easy to prove because the proof of this is, see, f less than or equal to g and So you will get the conclusion from it. I think that's a place where we stop. So we have seen that very, very comfortable. You can take the limit supremum, limit infimum, and limit if it exists of measurable x-limited real value functions. They are all going to be measurable. So you are in a very comfortable place once the sequence of functions have the measurability. So thank you very much.